Suppose the following function machine represents the function f of x equals 2 to the power of x, where x represents the number going into the machine and f of x represents the number coming out. Suppose we were to put in an x value of 1. Our machine would do 2 to the first power and output the number 2. What if we were to put in a 3? Our machine would do 2 to the third power and the number coming out would be 8. If we were to put in another number like 4, our machine does 2 to the fourth power, and we would end up with 16. Now, what if we were to think about going through this same function machine backwards? Let's say the number coming out was a 4, and we want to figure out what number was put in. We could think 2 to what power would equal 4, and that would be 2. Suppose the number coming out was 32. We could ask ourselves the same question. 2 to what power equals 32, and that would be 5. Maybe the number coming out is 2, so we could think 2 to what power is 2, and that would be 1. Recall that going through a function machine backwards gives the inverse function. The inverse function describes a rule that undoes the original function rule. There's a special name for the inverse of an exponential function. It's called a logarithmic function, or log function for short. The original function described by our machine was an exponential function, y equals 2 to the power of x. Within this function, the 2 holding up the exponent is sometimes referred to as the base. The logarithmic function, that is the inverse of this, would be y equals log base 2 of x. Notice how the word base is actually used when we say this aloud. These two functions are inverses. This one tells us what happens going forwards through the machine. This would be the function that undoes it, telling us what happens when we go backwards. For example, let's think about 2 to the fourth power. If we put a 4 into the machine, the number coming out will be 16. If we were to take the 16 and put it into the log function, going backwards, we would have log base 2 of 16, and the number coming out would be 4. We're ending up with the same number that we started with. Every equation written in exponential form can be rewritten in an equivalent logarithmic form. So here are a few more examples. Suppose our exponential form says that 2 to the third power equals 8. Remember, 2 would be the base. The logarithmic form would look like this. Log base 2 of 8 is 3. The base is always the smaller number right after the log. Another connection between these two forms, an easy way to remember, would be to draw a loop. If you start your pencil at the base, make a loop around the outside number, in this case the 3, and we're going to end at the 8. This tells us 2 to the third power equals 8, and that's exactly what we have over here for the exponential form. Going the other way around, we can use the loop again. If we wanted to write log base 3 of 81 equals 4, we could say it's 3 to the fourth power equals 81. And that one may sound familiar. We know that that is a true statement. Take a moment to try the next two on your own. I want you to pause the video, fill in your charts, and restart the video when you're ready. This one would be log base 6 of of 36 equals 2. Doing a quick check with our loop, we have 6 to the second power equals 36. The last one, starting down here at the base of 5, tells us 5 to the first power is 5. Thinking about everything we've talked about so far, we're going to look at a process for evaluating logarithms. First example, we have log base 4 of 64. When we evaluate, we're trying to figure out what this is equal to. So as a first step, we can set the log expression equal to x. So you actually have to write that part in there. Then we're going to turn the equation into exponential form, and you can think about using the loop. So we could write this one as 4 to the power of x equals 64. Then we want to rewrite both sides with the same base. In this problem, the left side has a base of 4. We could rewrite the right side with a base of 4 because 64 is the same as 4 to the third power. If you think about that chart that we glued into your notebook a few weeks back, it was a green chart. It had a list of common squares, cubes, fourths, and fifths. That may be a helpful chart to look back at when you're evaluating logs. Now that we have the same base, we're going to set the exponents equal and solve for x if needed. In this problem, if 4 to the x equals 4 to the third, then we could conclude that x equals 3. This first example was kind of an easy one. You maybe could think about this in your head without having to show the formal steps by thinking 4 to what power equals 64. So I want you to practice that. If you see some where the numbers are easy to do it in your head, go ahead and do that. But let's look at the next example. If we think about setting this equal to x and thinking 4 to some power equals 32, it doesn't perfectly align with the powers of 4. 4 to the first power is 4, 4 to the second power is 16, 4 to the third power is 64, and 32 is not in there. And so we will have to do a little bit more work on this one. So let's practice following the same process. We can do our loop to turn this into exponential form. Now for the next step, to rewrite both sides with the same base, it's not possible to write 32 with a base of 4 as we saw up here. But it is possible to rewrite both sides with a smaller base. They could both be written with a base of 2. If you think about the powers of 2, 4 is 2 to the second power, and 32 is 2 to the fifth power. So we can rewrite the left side, 4 as 2 squared. The exponent of x is still going to stay on the end, so now we have 2 to the power of 2x. Notice how this part and this part are the same. For the other side, we can write 32 as 2 to the fifth power. Now that we have the same base on both sides, we're going to set the exponents equal and solve for x. If 2 to the 2x equals 2 to the fifth, then we can conclude that 2x equals 5. We can divide both sides by 2 and we can get our final answer. You can leave this in the form of a fraction, or you can write it as a decimal. X would be 5/2 or 2.5. Alright, let's try the next one. Same idea. We'll start by setting this equal to x. We'll do our loop to get it into exponential form. Alright, so we have a base of 2 on the left side. It would be nice if we could get a base of 2 on the right side. Something that you might notice about the 8, we could rewrite 8 as 2 to the third. 1 over 2 to the third is the same as 2 to the negative 3. Remember that if you have a negative exponent, it turns into a fraction that has a numerator of 1, and the exponent becomes positive. We could turn that fraction back into a non-fraction by making the exponent negative. So if we bring down the 2 to the x, we see that we have 2 to the x equals 2 to the negative 3. We'll set the exponents equal to each other. No work is needed to solve for x. We can just say that x is negative 3. All right. The last one may seem a little strange. We have a base of 25 on the left, which is a bigger number. A bigger number raised to something is equal to a smaller number over here of 5. But if we think about getting these to be the same base, we could actually rewrite 25 as 5 squared. Again, keep the x on the end. Think about what the exponent would be for the 5. It's invisible. It's just an exponent of 1. 5 to the first power is equal to 5. Now we can set our exponents equal. Off to the side here we can show that if 2x equals 1, then x equals 1/2. Alright, finally we're going to talk about common logarithms. The logarithm with base 10 is so frequently used, it's often called the common logarithm or the common log, and it's usually written without showing the base. For example, if you wanted to write log base 10 of 17, you would just write log 17. In the next few problems, we'll see that the base is not shown. We can assume that it is a base of 10. Now, if we wanted to think about evaluating these, we could set them equal to x, draw the loop, and do the formal steps that we did above. But these are very easy to think about. If we put in the invisible base 10, we could think 10 to some power equals 100, and that would be 2, because 10 to the second power is 100. Try the next 3 on your own. You can pause the video and restart it when you're ready. The next one, log of 1,000, which is really log base 10 of 1,000, would be 3, because 10 to the third power is 1,000. Log of 10 is 1, because 10 to the first power is 10. And for the last one, if we want to make this go into a fraction, we would have to have a negative exponent. In this case, it would be negative 1, because 10 to the power of negative 1 would be 1 over 10 to the positive 1, but because it's just a 1, we don't typically write it in there, so you could erase it and just write it as 1/10.